Hi, and welcome to this latest video in our lecture series on computational finance. My name is Gregor Weiss. I'm a professor of finance at Leipzig University, and I welcome you to this latest video in which I will talk about the iterative solution of systems of linear equations. In the previous videos, we've seen direct methods to solve systems of linear equations. Most notably, we've seen Gaussian elimination that you might remember from your high school, for example. Now, in direct methods for the solution of systems of linear equations, we are trying to find one solution in one or more steps. In iterative methods, in contrast, we are trying to use a starting solution, a start value or a start vector, and then we iteratively change this solution, and we start, for example, with x0, then we have x1, x2, x3, etc. And thus we have a sequence of iterations and a sequence of solutions that we want to improve upon in every iteration until, hopefully, the sequence converges to solution xn, xt, however we want to call this, and this might be due to the fact that the sequence has converged, or that we've simply run out of time or patience and we've decided, okay, the changes between, for example, xn and xn minus 1, between two iterations, the change is so small and negligible that we decide, okay, we can now cut it off, we stop, and we just accept xn as our solution for our problem. Now, theoretically, the method could be continued infinitely, so that usually we have a maximum amount of practicable iterations, a maximum number of calculations we want to make, a tolerance level for the change between two successive values. So there must be a stopping condition when we want to stop this iterative procedure. For solving systems of linear equations, we actually have a number of methods that are at our disposal. Now here, I want to concentrate on the relatively simple Gauss-Jacobi method, and some other examples for iterative methods are, for example, Gauss-Seidel or the SOR method. Now, the iterative solution for solving systems of linear equations are particularly advantageous for problems where we have sparse coefficient matrices. For example, in some aspects or in some constellations in, for example, production management and supply chain management, we actually have huge matrices that are sparse, meaning that most of the entries are zero, and there are only a few entries in these coefficient matrices that are non-zero, meaning that we could do a lot of calculations using a direct method, but all these calculations, all these computations would actually be 0 times 0 times 0 plus 0 times 0, result being 0. The computer would do this every time, and thus we would waste a lot of computational effort and a lot of time, whereas iterative methods will hopefully converge quite quickly because they will see, okay, the matrix has this structure and we have a lot of zeros. So this is where we usually apply iterative methods for solving systems of linear equations. Let's start with Gauss-Jacobi. The system of linear equations is given by a times x equals b, and we write a as d plus c, and d being a diagonal matrix. So we split up a, the coefficient matrix, into the diagonal, the main diagonal, and the remainder. So that's d and c. Thus, we can write the system of linear equation, it's equivalent to d times x equals minus c times x plus b. And thus the iteration condition for the Gauss-Jacobi method is simply given by minus d, so we have to multiply this here with the inverse of d from the left. So we are putting minus d in front here, and thus it becomes x. And, sorry, actually, not minus, but just d inverted. And then we have to multiply d inverted in here and also in here, and thus we get x equals d inverted times c times x plus d inverted times b. And we are now switching from x and x to xn plus 1 in the next step, and here with the previous solution xn. And the iteration sequence for the Gauss-Jacobi method converges provided that the spectral radius of this matrix here is smaller than 1. I'm not going to prove this. You can look it up in the corresponding textbooks on numerical analysis, but this is actually the Gauss-Jacobi method with a very, very simple iteration condition. Just take the matrix A, split it up, and then you have to invert D, multiply it with C, and then you have the iteration sequence. Let's do this in MATLAB. We define a function called Jacobi. We will give this function, the matrix A, the vector B, our starting vector, an epsilon or a maximum number of iterations. So either the sequence doesn't change too much, then we will abort the whole program using, epsilon, or we've run out of iterations and let's say we'll use 1,000, 10,000 iterations, and then the algorithm is supposed to stop. dA is diag of A, so we extract the elements of the main diagonal as a vector. C is A minus the diagonal matrix of dA. D inverse, or D-inf, is the diagonal matrix D inverted, which is quite simple because it's a diagonal matrix, and diagonal matrices are simply inverted by inverting all the diagonal entries of that matrix. B is then given by minus D-inf times C. B1 is D-inf times B. So it's just a number of lines in which we multiply the different vectors and matrices so that we don't have to include this in the main for sequence. And thus old x is initialized using x0, our starting value. And then for I being 1 to the maximum number of iterations, the iteration is x equals b times old x plus b1. So as you can see, this is just d inverted times c with a negative sign. And if the norm of x minus the previous solution is smaller than epsilon times the norm of old x, break, and then end. And if this is not fulfilled, then reinitialize the next vector into the previous vector, and we move on in the sequence of iterations. Let's do this for selected matrices. So A1 and A2 are two 4 times 4 dimensional symmetric coefficient matrices. B is 1, 4, minus 2, 1. And we can get more or less the exact solutions using the backslash operator, which is Gaussian elimination. So exact 1 and exact 2 are the solutions we would get using a direct method. And then we calculate the solution using the Gauss-Jacobi method, and we use A1 and A2, a maximum number of 10,000 iterations, and we want it to have a minimal change of at least 10 taken to the power of minus 8. So 8 decimals is the change that we still accept. If it's smaller, then we will stop the algorithm. X1 in this case is 0.5556, and we get basically the same results using the iterative method. In the second case, we have x2, which is 10 to the power of 27, and this is completely off. And we can easily see what happens. First, we only need 41 iterations in the first case for the first system of linear equations, and we've run out of iterations in this case, and the algorithm just stopped way before converging. And you can guess what the reason for this is. The sequence converges for the Gauss-Jacobi method if the spectral radius of this matrix here is smaller than 1. And guess what? In case of the second matrix A2, we calculate the matrix we take the eigenvalues, the absolute maximum absolute eigenvalues of the spectral radius, and we can see in case of the first matrix, the convergence requirement, the condition is fulfilled. In the second case, it's barely not fulfilled. So this is why the Gauss-Jacobi method in case of A2, the second system of linear equations, it fails. So we need to check this first, otherwise we run into this kind of problem. So that's an iterative method for solving a system of linear equations. And in the next videos, we'll start with the capital asset pricing model and some examples for portfolio optimization. Thanks for watching, and if you've liked this video, consider subscribing to our channel. Thanks.